we are going to refresh our memory on the absolute value function. And we're going to look at a new transformation. So we're going to start with the absolute value of a number is the distance from 0 on the number line. So if I wanted the absolute value of -9, what is the distance from 0 to -9? 9. So absolute value is non-negative. Okay, absolute value is non-negative. So we looked at this absolute value function before, so it's worth looking at it again. This is called a piecewise function. So when I plug in -2, the absolute value spits out 2. When I plug in -1, absolute value is 1. When I put in 0, it spits out 0. When I put in 1, I get 1. When I put in 2, I get 2. So that's 0, 0, 1, 1, 2, 2. And notice this is a V. It has a pointy corner. An absolute value function has what we call a vertex, and that's at that corner. So we're doing the parent function for absolute value of x. Let's talk domain and range. That's always an important piece of information on a graph. What is my domain? How far left and how far right can I go? Davey? Nice. Okay, so absolute value functions. The domain is always -infinity to infinity. Now the range will vary from problem to problem, but for the parent graph, what is my range? What's the lowest y value, comma, the highest value? Yeah, 0 to infinity. All right, so now all the transformations we've done so far, they apply to no matter what parent function we have. So look at example 1, letter A. Just based on our knowledge, if I have f of x equals the absolute value of x minus 5 minus 3, who wants to take an attempt at what would be our shifts? What's happening here? Ellie, what do you think? Yep, right 5. No, just right 5 because we've replaced the x with the x minus 5. And then what does the minus 3 do? Good job. Okay, so it's down 3. So remember, the inside is the left-right, opposite of what you think. The outside is up-down, exactly what you think. So my vertex from the parent function went right 5 and down 3. So where do you think my new vertex is located? Yeah, Charlie? Awesome. 5, -3. So what you can do then is we can take these 5 points. So that was in my middle row. And all you're going to do is take every single point and move it right 5 and then down 3. So 1 is going to go to 6, 2 is going to go to 7, -1 would go to 4, -2 is going to go to 3. I'm going to move all the x values right 3, and we're going to move all of the y values down 3. So 2 minus 3 is -1. 1 minus 3 is -2. So let's plot this. Here's 3, -1, 4, -2, 5, -3, 6, -2, 7, -1. Okay, do you see I'm using this parent function? These are my table. So I'm saying from the parent graph, y equals absolute value of x, I took every x value and I moved them right 5. So -2 plus 5 is 3, -1 plus 5 is 4, 0 plus 5 is 5, and then I took the y values and I subtracted 3. 2 minus 3 is -1, 1 minus 3 is -2, 0 minus 3. Do you see that? Yeah. Okay, so let's talk domain and range. What's the domain here? It's always the same. Yes, there you go, nice. -infinity to infinity. Now the range. What's my lowest y value now? -3. Okay, I want to introduce a notation here, and it's called mapping notation. And mapping notation for this particular problem, we use a capital T for transformation, and it looks like this. Capital T of my point xy, well, what did we do? We moved every point right 5, so we're going to add 5 to every x value, and we're going to subtract 3 because we moved down 3. Now I want you to pause a moment because this is where it can get muddy. This is where it can get confusing. Do you see that in the equation, it's x minus 5 moves it right 3, but in mapping notation, it's really x plus 5? So notice that difference, but then the y stays like it should. All right, let's do another one. So my vertex is moving from 0, 0 to where? Up 4. Nice, okay? So that's going to be 0, 4. But that negative out front is a reflection over the x-axis and then up 4. So this is where the mapping notation helps. So what you're going to do, reflections happen before the up. Okay, reflections happen before the up. So I didn't do anything to x, but you're going to take the opposite of y plus 4. All right, so watch what we're going to do. We're going to be looking at the parent graph. Okay, we're going to look at the parent function here, the -2 to 2. My x values are the same. So we're just going to go -2, -1, 0, 1, 2. Nothing happened to the x values. But my y values, what you're going to do is you're going to take the opposite of the y and add 4. Okay, you're going to take the opposite of y and add 4. So I'm going to take the opposite of 2, which is -2, plus 4. So that's 2. The opposite of 1 is -1 plus 4 is 3. The opposite of 0 is 0 plus 4. The opposite of 1 is -1 plus 4 is 3. And the opposite of 2 is -2 plus 4 is 2. So then let's plot this. And you are encouraged to continue the dots, like once you figure out the pattern. Yeah. Okay, so the negative is not inside with the x. So technically, we could have had this as, whoops, as f of x divided by -1 equals the absolute value. Well, then I'd need to do -4, but yeah, the negative is in front of the function. It'll be a reflection over the y-axis if it had been absolute value -x. Okay? All right, let's talk domain and range. Domain is always -infinity to infinity. Uh-oh. What happened with the range when you reflect? Yeah, now we're going to start -infinity. And what's that highest y value? 4. Now here, if you haven't already kind of connected the dots here, pun intended, do you see my vertex? The y value of your vertex is always going to be one of the numbers in the range. And it'll either go to positive infinity or negative infinity. You see that? This vertex in part A was -3, but it went up. All right, let's look at this one. And if it helps, let's maybe in the middle put the parent function again. Okay, this is y equals absolute value of x. All right, let's just start plugging in some values and see what happens. Do you see that there's no left-right on this one? Okay, there's no left-right. So let's plug in 0, and I'm plugging it into this equation, y over 2 equals the absolute value of x. If I plug in 0, what's y? If x is 0, what's y? 0, okay. Now what happens if I plug in x is 1? Well, you'd get y over 2 equals the absolute value of 1. Well, what's the absolute value of 1? It's 1. And then you'd multiply both sides by 2, and y is 2. So do you notice that I doubled the y value by doing that? Let's try 2. Let's plug in x is 2. So we get y over 2, and let's do that part in our head. Absolute value of 2 is 2. You multiply by 2, and y is 4. Now there is symmetry. Did you notice that? As long as I keep it where I didn't move it left or right, I have symmetry there. So let's graph this. I have 0, 0, -1, 2, -2, 4. So do you notice that instead of going right 1, up 1, or up 1, right 1, I went up 2, right 1? So on the y-axis, I went up further. This is referred to as a dilation or a vertical stretch of 2. So I wanted us to sort of discover what was happening. Okay, I wanted us to discover what was happening. And so in mapping notation, what we actually did is we did nothing to x, but we doubled the y values. Do you notice that in the table? I could have taken the the y values and just doubled them. All right, let's try this again with let's do our domain and range. Domain is negative infinity to infinity, and my range is 0 to infinity. So a dilation or vertical stretch did not change domain and range from the parent function. It was the same. All right, let's take a look here. And, okay, now I've got something in here inside. So 0, 0, 0, 0 is going to be the same. But do you see if I put in that x is 1, I get 1/3? And that's yucky. Okay, that's actually yucky. So the first nice number after 0, what happens if I plug in that x is 3? What would be the y value there if I plug in x is 3? 1. Oh, isn't that nice? What would be the next nice number to try? 6, right? 6. Because you would get 6 over 3, which is 2. So then we can go on the other side. Negative 3. Well, negative 3 over 3, even though that's negative 1, when I take the absolute value, what is that? It's 1, and then that'll be 2. So let's plot this one. Here's 6, 2, 3, 1, 0, 0. Okay, this one, do you see that I actually spread out on the x-axis now? To go up 1, I had to go right 3. So this is called a horizontal stretch of 3. And my mapping notation would look like this. What did I do to the x values to get the parent function y values of 1 and 2? Didn't we multiply them by 3? Like 3 times 1 is 3, 3 times 2 is 6. So my mapping notation would be t of xy gets mapped onto 3x comma y. Now the good news is we're going to spend 2 days on this, so I know this is a little bit confusing or a lot confusing. So don't worry, we're gonna spend 2 days on 3.6. We'll see if we can't get it ironed out after tomorrow's class. But just sort of stay with me, and then you might want to read through the notes again or watch this video. All right, note, translations and reflections are called rigid transformations. They produce an image that is congruent to the original figure. Vertical and horizontal dilations are non-rigid transformations. The image is not congruent to the original figure. So here I want you to use your highlighter. If you replace y with y over b, then that will dilate the graph by a factor of b vertically. If you replace x with x over a, that will dilate the graph by a factor of a horizontally. So let's pause a moment and look back at our example 1. So I had y over 2, and that dilated vertically by a factor of 2. In part B, I had y equals absolute value x over 3. So that dilated or stretched the graph horizontally by a factor of 3. A dilation is a transformation that expands, we call that stretches, or compresses or shrinks a graph either horizontally or vertically. Given the graph of y equals f of x, y over b equals f over x, or sometimes you can multiply it and make it y equals b times f of x, is a vertical dilation of a factor of b. Now, if b is bigger than 1, it's a stretch, and if b is a fraction between 0 and 1, it's called a shrink. If b is negative, it's a reflection over the x-axis. If you have y equals f of x, and you have f of x over a, that's a horizontal dilation by a factor of a. If a is bigger than 1, it's a stretch. If a is between 0 and 1, it's a shrink. And if a has a negative in front, then it's a reflection over the x-axis. Now, this dilation applies to all parent graphs we've ever seen. So in example 2, letter A, do you see there's no parenthesis around the 3 and the x? This is not, some of you have been using improper math notation. This is not the way we say the quantity 3x squared. That's not what we have. So I can divide both sides by 3. And according to this right here, if you have y over b, it's a dilation vertically by a factor of b. So this is a vertical dilation, and we're going to call it a stretch because it's a number bigger than 1, of 3. You see that? B is 3. Now, in part B, I'm going to rewrite 0.5 as 1/2 square root x, and then watch this. If I divide both sides by 1/2, this is a vertical shrink of 1/2 because that b value is in fact 1/2. It has to be y divided by a number to be able to describe it. So this part's confusing about the fractions, okay? So for now, stay with me, write it down, and we'll iron it out. It'll be okay. We'll get it. So let's look at example 3. Describe what happens to the graph of y equals f of x when it's transformed into 3y equals f of x over 2. Well, what I need to do is I have to rewrite this as y over 1/3. And maybe we need to go back to about 5th grade math with dividing by fractions. Do you remember that y over 1/3 is the same as y times 3 over 1? Like, that's why that's true, okay? This is just back to some elementary math. So let's do this. What is b? Remember, it had to be y over b. So what's my b value? 1/3. So that makes it a vertical shrink of 1/3. What's the a value? It's f of x divided by a. So what's my a value? Two. So that makes it a horizontal stretch of 2. So again, this is a lot of information we've taken in today. Let me go back over it one more time. If you have y equals f of x, and you take y and divide it by b, that's a vertical dilation of factor b. If b is bigger than 1, it's a stretch. If b is between 0 and 1, it's a shrink. if you take y equals f of x and you take x and divide it by a, that's a horizontal dilation by a factor of a. When a is bigger than 1, it's a stretch. When a is between 0 and 1, it's a shrink. All right, let's look at example 4. It says, write an equation for the function that results from translating y equals absolute value of x, left 3 units, and a vertical dilation by a factor of 2. So watch this. Vertical is in the y spot. So I'm going to put y over 2 equals left 3 units. That's absolute value of x plus 3. All right, in general, the graph of an absolute value function of the form f of x equals a times the absolute value of x minus h plus k can involve translations, reflections, stretches, or compressions. To graph an absolute value function, start by identifying the vertex. You can use a as the slope, and if you have to pay attention to whether it's positive or negative. So let's look at example 5. So I'm first going to rewrite this. Well, no, okay, so can you tell what the vertex is? This is it's been shifted left 3, down 4. Now this 1/2, do you understand that you would have to divide by a half? So that's going to be a vertical shrink. That 1/2 is not inside with the x, okay? It's on the outside. So this is a vertical shrink of 1/2. So my vertex went from 0, 0, and I moved it left 3, down 4. And then the a value can act like the slope, or we can do this. We can do our mapping notation, and we're going to take the x value and move them left 3. We're going to take 1/2 of y and then move it down 4. So I like to do my parent graph and then send it through the mapping notation. So we already did the -3, -4. That was the vertex. So all of my x values are getting moved left 3. So that's -2, -1, -4, -5. All I did is I took the parent function, the -2 to 2, and I moved all the x values left 3. Then I'm going to take half of the y values and subtract 4. So I would take half of 2, that's 1. 1 minus 4 is -3. Now there's symmetry, so then I can go to the other end of the table. Then 1/2 times 1 minus 4, isn't that -3.5? So I'm actually not going to plot those fractions, the decimals, because I can get it with going to -5, -3, and -1, -3. Like that's going to be enough for me to draw the V. Okay, let's do the last one. It says write the equation of the absolute value function. Where is the vertex? 3, 0. So I can tell my vertex has been moved right 3. Then, if you notice, I would have to go up 1 and right 3. Up 1 and right 3. So this would be a vertical shrink of 1/3. Yeah. Okay, so I'm plugging in the y value is 1. So I took half of 1. I'm using this mapping notation, and I'm only looking at the y coordinate. So I took half of 1 minus 4. So that's 1/2 minus 4, which is negative 3.5. Wow. Okay, so your job is to attempt the 3-6 worksheet 1. Get into Math Lab if you need help, and then we'll definitely go over this.